This is a conservation of energy example, and we're going to work through this so we can see how you can use conservation of energy to solve a problem. So we have a spring clamped to a table, and at the end of the spring is a ball of mass 20 kilograms, and the spring is compressed 20 centimeters. The ball is released from rest, and the ball will accelerate to the right. It will get to the end of the table, and then it will be a projectile, and it eventually falls a distance of 5 meters away from the table. How we're going to solve this problem? Well, by the way, we're asked to solve for the spring constant. Now, we're first going to treat this as a kinematics problem. We're going to figure out the speed at which the ball is going at the moment it leaves the table. So we're going to label that position 2. Position 1 is when it's compressed, and position 3 is when it hits the ground. So let's figure out the time it takes to go from position 2 to position 3. So time to go from 2 to 3. Well, we know it travels a distance of 5 meters in the horizontal direction, so time is distance, which is 5 meters, over the horizontal speed that the ball is going at position 2. Remember, this is a projectile once it leaves the table, so its horizontal speed is constant. So the horizontal speed at 2 is going to be the same at 3. So this is a representation of the time it takes to do that. Now, we also know that it falls a distance of 1.5 meters. So we can actually solve for the velocity, or the speed at position 2, using another kinematics equation. So in the y direction, our change in y is going to equal our initial y speed times t plus 1/2 times our acceleration times t squared. Delta y in this equation is minus 1.5 meters. Our initial y velocity, speed, is 0. So this negative 1.5 is equal to 1/2 times 9.81 meters per second times our time squared. So that's 5 meters over v2 squared. Okay. Note in this equation we know everything except v2, so we can solve for v2, and I'll let you verify this, but if you do everything correctly you should get 9 meters per second. So that's the speed that the ball is going once the spring is back to its equilibrium position. So now we can turn to conservation of energy. So let's figure out the energy at position 1. That's going to be our initial energy. So E1, it's the sum of our mechanical energy, it's the total mechanical energy, which is the sum of our potential energy at 1 plus our kinetic energy at 1. And since the ball is released from rest, our kinetic energy is 0, and we just have potential, which is, in this case, it's not m, it's the potential energy stored in the spring, which is 1/2 times the spring constant times the distance it's been compressed. Now we need the energy at position 2. At this position it's all kinetic. This ball hasn't started to fall yet. It's at the edge of the table, so it doesn't fall. It hasn't fallen yet, and the spring is back to its equilibrium position. So the energy at 2 is equal to, again, the sum of the potential and kinetic energies. Our potential energy now is 0, and we just have kinetic energy, which is 1/2 mv2 squared. And conservation of energy says that our energy at 1 has to equal our energy at 2. So we get 1/2 k x squared is equal to 1/2 mv squared. We can simplify this. We can multiply both sides by 2 and solve for k by dividing both sides by x squared, and we obtain mv squared over x squared. And plugging in our values, the mass was 20 grams, so that's 0.02 kilograms, times the speed of 9.0 meters per second, and we square that, divided by the x, which is the distance the spring was compressed, and that is 20 centimeters, so 0.2 meters, and we square that. And I believe just two significant figures, you should get k to be 41 newtons per meter.